people could join. And
So I've got my, okay, I see it says now streaming. Now I'm getting the McDonald's ad also. Okay, I got it.
yeah, everybody's gonna get an ad, I guess.
Yeah, you get a
Uh,
double cheeseburger. $3 bundle.
if you want to get a cheeseburger, you should get a cheeseburger. But
I like cheeseburgers.
I like cheeseburgers too. But I would actually argue that advertising, just I don't understand how it works because advertising never affects me. Like I never see somebody drink a Coke and then go, "I wish I had a Coke right now." I mean, if I want a Coke, I just get a Coke, right?
Well, I mean, maybe there's a delayed onset for the effect.
I
Maybe when you're at the supermarket, you don't really go there for Coke. When you see them, you're like, oh, what would be good? Coke.
I
But
mean,
it got you.
we're not being sponsored by Coke. I should just point that out. But
Right.
like the uh, the effect of advertising doesn't. I just don't understand how it works. Like it must work on some people. Like some people out there must see that and think, I want that right now. Like I saw
Yeah.
a Taco Bell ad and I want Taco Bell right now. Whereas like I see it and I think, oh cool, Taco Bell has some sort of new food I'm not going to eat.
Right.
You know,
Right. But you know where it never works on me either is the movie theater. Like how they have like the Coke or the popcorn flying in and out, like just before the movie starts. And I suppose that's supposed to motivate you to get up and get a snack.
hey,
Never.
Sarah made an account.
Did she?
Yeah, because she's in the channel chatting right now. She says it works with burgers and it also works with Taco Bell.
Oh, great.
Hi, Anarchy Kitchen. How's it going? Anarchy Kitchen is another fellow streamer, and
Cool.
they cook live
Nice.
on the streaming,
Oh,
and
cool.
sometimes they just sharpen knives and stuff. But he was doing a really cool thing for like I don't know if it's still going on, but he was like moving around Africa from one country to the next, basically every time he would stream cooking a different meal from a different country in Africa,
Oh, that's
and
great.
super cool idea.
Yeah.
So sometimes I'll have to stop and do this too. Like I do a little shout out to people. So you can see into the channel right now, Mike. Yep.
Uh, yes, I believe I can. I
Okay.
am. I'm seeing it.
There you
Yeah,
go.
I'm seeing it. And when I pull up Twitch, yeah, I am.
Yeah. Okay. So we're just doing a little pre-interview chat. Feel free to chat in the channel as well. And this is my guest, Dr. Mike McGlue. And we're really intently talking. I don't think the whole interview will be about hamburgers or cheeseburgers, but if
But
it
it is
is,
a natural springboard.
yeah, I mean, we can go right from talking about hamburgers and cheeseburgers into food security at Lake Tanganyika for sure.
Obvious transition.
That, yeah,
It's
completely.
interesting. In Tanzania, when I first started working there, it would have been 2005, and there were no fast food restaurants of any kind in the major city, Dar es Salaam. Fast forward to the past few years, I guess 2018 was the last time I've been to the lake to work, but I was there from 2014 to 2018. And now there's a Kentucky Fried Chicken and a couple of other fast food restaurants, which are, quite popular, as I understand.
The Colonel is there?
It's huge.
Really?
It's huge. Yep, there's like a line out the door every day. People love fried chicken, and why? Who could blame them? It's fantastic.
Um, I mean, I guess I don't
Huh?
have a problem with fried chicken.
You don't crave it as much as cheeseburger.
Um, I I don't think I've eaten fried chicken in quite a while. A cheeseburger I've
Really?
had relatively recently because I can make myself a cheeseburger, but
Right.
I can't really make fried chicken.
If you get one of those little fry daddies,
I'm sure
you
there's a way
can
to do it. I'm
you
sure.
can have chicken tenders any day of the week if you want them.
Probably it's the wanting it that doesn't happen as much because if I
Mm,
did, I probably have the resources and could figure it out.
definitely.
But
Well, it's at any rate, it is very popular there for some reason, and you would think, McDonald's would be an obvious one to be kind of like the first foot through the door if you're going to open up the fast food market in a major African city. You would think McDonald's, but no, fried chicken.
Huh. So Mika, who's one of our people in the chat, says your name reminds them of MacGyver, except you can solve anything with glue.
Oh, thank you.
McGlue.
Sure.
Yeah.
Yeah.
What
I'm
couldn't you
looking.
solve with glue is a good question.
I mean, I'll say this: I haven't bought glue in some time. It's one of those things that you buy it once and it can sit there for, a decade.
It's like me and fried chicken, except for fried chicken can't sit there for decades.
Well, yeah, it depends on where it's from.
I mean, it could sit there for decades, but it doesn't mean I'm going to eat it afterwards.
Unlike a McDonald's cheeseburger, right? Which has there have been tests about its fidelity after a decade, and it's virtually identical to when you purchase it.
I mean, I really appreciate a burger that can withstand decades.
Sure. I mean, I suppose.
All right,
It's
well,
interesting though, and I actually was thinking about this. The first authors of the articles, McGlue, Ivory, and Stone. It's got a nice ring to it. It's in a weird way elemental.
you in pre-chat we were talking a little bit about who might be here, and Tuma is here.
Oh,
He
hi tuna.
he's in the chat. He says Chips Cuckoo in Dar is the best fast food.
Chips
Chips
cuckoo.
Cuckoo.
Yeah, that would be chicken and French fries.
Is that what it is?
Mm-hmm.
Oh, well,
Cuckoo is the word for chicken, Swahili, and chips is French fries.
lots of languages, I guess. Chips are French fries,
Mm-hmm.
except for ours, where chips are chips.
Right.
Well, I guess we could get to the part where I'm supposed to be asking you questions and you're supposed to be answering them anytime now.
Sure. Sounds good.
So we're trying to keep it as a casual interview, of course. And a lot of the people who might be checking in to see the interview don't really know like what you do. So if you could try to explain what you do as a scientist in a language that your parents or maybe Sarah's parents, if they're listening, could understand. I'm sure Sarah's parents probably already know what you do, but
Well, I guess the simplest way to say it is that I'm a scientist that studies lakes, right? And um, sort of in the same way that a historian, you know, delves into archives and turns pages in a book and tries to understand old information. I look at layers of mud that accumulate on the bottom of a lake and try to read each of those layers and learn something about the history of that particular lake and that particular setting. And it turns out that lake sediments are oftentimes very useful for that purpose, where you can actually learn something very specific about climate or water or changes in organisms living around the lake or within the lake from signals that we can read in mud.
and what part of that specifically do you study?
I do a bunch of different things. I look at the composition of the muds from a geochemical perspective to see what sort of elements make the muds up. And I also look at the stratigraphy of the mud, in other words, how they stack up in time, and also try to understand the time over which those sediments were deposited, how much time is represented. For a lot of the stuff that we do, um, knowing the time is super important, right? If we want to understand history, we need to know as precisely as we can what time things were occurring. And so that's another one of these great benefits of working in lakes, because lakes are often um, sedimentary systems that we can actually date with some accuracy using tools like radiocarbon, for example.
So maybe more generally, then, what kind of questions could your research answer? Like,
Oh, lots of different things. In East Africa and at Lake Tanganyika in particular, a lot of my work is focused on questions related to conservation, right? Particularly the studies that we do that look at very recent timescales. we're interested in using different aspects of lake sediments and lake deposits to think about things like sediment pollution, for example. Right? There's kind of three major things that are affecting Lake Tanganyika and its fishery right now that oftentimes you'll hear about. And the big three are climate change, overfishing, and pollution problems, in particular sediment pollution. So a lot of the work I've done recently has been aimed to try to address each of those three questions. So from the sediment pollution perspective, we can look at how fast sediments are accumulating in a particular part of the lake and their thicknesses and how they're distributed, and relate that to what's going on onshore, for example, through agriculture. Right? In terms of the overfishing problem, one of the ways geologists like me can plug into that is by helping to define protected zones in the coastal areas. And we do that by using geophysical tools to map out special places that fish use to breed and spawn. Right? So it turns out that a lot of the economically important fish that people eat on Lake Tanganyika, they live offshore in kind of the deeper water areas, but all of them come into the nearshore area to have their babies. And almost all of them like to have their babies in areas with rocks on the lake floor. They like rocky substrates, is what we call them.
Who
And
doesn't?
yeah, and so it turns out that those environments are highly variable. They have, like, algae growing on the rocks, and they have different levels of light. So they're kind of good places for young fish to hang out. But because the lake is so big and it's pretty much unstudied in a lot of ways, we don't always know where those rocky substrates are. So we can actually go in and map them, and then tell people living there, hey, don't fish these particular areas because this is kind of the spawning ground for the fish. And so that's how we're plugging into the overfishing problem, and of course the sort of studies that you and I have done in southern Lake Tanganyika, along with some others here, are looking at the climate change question and how climate influences the lake and its fishery. So we plug in a lot of different ways. And kind of the long term, from looking at the lake from longer perspectives, Tanganyika is really cool because it's a really, really ancient lake. And there's probably, several million years of sediments that have accumulated within the deepest parts of the basin. And one of our long-term goals is to try to collect some of those older sediments and learn how tropical climate, for example, has changed over much longer timescales. So there's a lot of different things that we do to plug in and study Lake Tanganyika, and there's a lot we can actually learn by applying pretty basic geological techniques.
The Lake Tanganyika is really kind of an interesting place. One of the viewers, Anarchy Kitchen, is asking how deep is the lake, and in general, I guess, on average.
It, it's really deep. It's like the second deepest lake in the world, and the deepest part of the lake is almost 1,500 meters deep, which is like real, like almost like deep water ocean depths. It's very, very deep. Um, Now it's not that deep everywhere, of course, but at its deepest point, it's almost 1,500 meters.
Yeah, and for people who don't know metric, what is that?
Um,
Roughly a mile, right?
yeah, yeah, almost 5,000 feet, right?
Yeah,
So it's quite deep.
yeah. So basically a mile straight down, filled with darkness and potentially lake monsters.
Yeah, yeah. It's like I said, it's hard to know. I mean, that we don't even really have super accurate maps of how deep the lake is, and it's kind of amazing to think in 2020 that one of the biggest lakes in the world and a place that people are seemingly very interested in, we don't have a lot of basic data in great detail, and so that's one thing that would be nice to change in the next, you know, over the course of our lifetimes.
The deepest lake in the world is Baikal, right?
Hmm.
And
Yep.
Baikal has really had a lot of scientific attention focused on it. It's been the center of just like a ton of research, but really only in the last maybe 2 decades.
Yeah.
But it would be nice to have that, I think, probably the same level of focus for a lake like Tanganyika that has this sort of location that is so important. And like Lake Baikal, Tanganyika has a really interesting, diverse biological component to it, in particular the fish, but maybe also many of the other organisms. Can you talk a little
Yeah,
bit about the fish?
I'm sure I mean, like you said, there's lots of really, really interesting life in the lake. And part of the reason for that is because the lake is so old. There's been a lot of opportunities for different types of organisms to evolve there. And so in the shallow waters, the fish are predominantly cichlids. And so probably some people will be familiar with them from aquariums. You find East African cichlid fish that are sold here in the aquarium trade all the time. And so they're these very brightly colored, a couple of inch long fish that do quite well in rocky habitats. So they make great aquarium fish because they're super colorful and they're quite pretty, and they're relatively easy to care for. And there's hundreds of them, and those fish are many of them are unique to Lake Tanganyika. Offshore, there's only a handful of fish that are kind of truly in the pelagic part of the system. There's a couple of different types of Nile perch or relatives of the Nile perch. There's a couple of sardines, and that's pretty much it. It's not too diverse in the open water environment.
One of the viewers, CalcMath, asks, "Is Tanganyika part of the Rift Valley?"
Yes, it absolutely is. It's in the Western Rift. So East Africa has two rift valleys that are somewhat connected. There's an Eastern Rift and a Western Rift. You can remember them because the Western Rift has the really big lakes and the Eastern Rift has all the volcanoes. And so the Western Rift is where Tanganyika is, and that's part of the reason why it's so deep. It's because it's in a very deep rift valley.
Um, how long? Oh, so I have a question about your position. I guess what do you do?
Mhm.
You're a professor um, at the University of Kentucky, right?
Right.
Can,
At the University of Kentucky, I've been here 7 years now.
can you talk a little bit about like what you teach or what you do there?
Sure. So I'm a professor, like a lot of professors at state universities. Our jobs are um, we do a couple of different things. One of them is research. One of them is teaching and advising of graduate students. Then we do various service things, serve on committees at the university and things like that. So I teach mostly in the field of sedimentary geology. I teach stratigraphy to undergraduates and graduates. I teach an advanced sedimentology class. I teach some undergraduate classes in environmental geology. So it kind of runs the gamut. It's pretty broad in terms of what topics I cover. I teach a mid-level class in geomorphology. I teach anywhere between 3 to 4 classes per year, and then I have a lab that I do research in, kind of another focus of the job, and that's a lab that has, I think, 5 or 6 graduate students typically at any time who are trying to do some research so they can get an advanced degree.
So we have a pretty good idea why we might want to do science in Tanganyika. You kind of covered those topics, but can you talk a little bit about how long you've been working at Lake Tanganyika?
Sure. I started working in Eastern Africa as a master's student, and that was in 2000, pretty much 2001 to 2003. I lived and worked in Uganda, and I was working on Lake Albert at the time, which is another rift lake to the north of Lake Tanganyika. And then when I started my doctoral degree in 2005, I came back to Eastern Africa and started working in Tanzania on Lake Tanganyika. And so I've pretty much worked there ever since. Although I don't necessarily go there every year. I've probably been to Lake Tanganyika a dozen times or so over the course of the past few years. But I don't necessarily go every single year. Sometimes I'll make multiple trips per year depending on what the needs are. So it's a place that I'm fairly comfortable working in. I've been there many times at this point, and it's quite a nice place to work actually.
I've never been to Lake Tanganyika, if you can believe that. I've been to Lake Malawi, but just been to Africa a few times, and I work in Africa, obviously, alongside with you on some projects, and also on some other projects that you're not involved on.
Mhm.
But so you know, the first time I went to Africa I was just a little sort of terrified about what might happen because I just didn't know anything about what it was like, and but can you talk a little bit about what doing field work is like in Africa? Because that sounds like it could be really scary.
Yeah, it's it's really fun. I have to say it has changed somewhat over the years. When I first went to um, Eastern Africa as a graduate student, there was a lot less development than there is today. And so, where you see the development is mainly in the eastern side of Tanzania, close to the major city centers. And the western part where Lake Tanganyika sits and where we work is quite remote and remains quite remote. It's quite distant from any kind of a major city, but it is increasingly more connected. There's better internet access. You can get there by plane now with relative ease. There's a much more reliable train line than there used to be. There was a time when it would be a 5 day train ride from Dar es Salaam, the capital, to the lake. And, if the train was on time, it would be 5 days. I've spent as long as 2 weeks on that train and waiting for breakdowns to get fixed. And so there was a time when just like physically getting to the lake was a great challenge, whereas today it's quite a bit better than it used to be. But it's still quite rural, particularly in and around the lake. It is a challenge um, because there's a lot less facilities than what we're typically accustomed to here. But I really like it. It's a really beautiful place, and the people are very nice and very welcoming, and we have a very strong group of people that we work with pretty much all the time. And so that part has been really excellent because you build relationships with people over decades, and it's like now it's kind of like going home in a way when you get to Kigoma, which is the main port town that we tend to work out of.
Oh, I think I lost your sound.
Did you? Can you hear me?
Oh, you're back.
Okay, sorry about that.
That's all right. Um, let's see. So, what about? Do you have any sort of crazy field stories that you want to share? Not necessarily about this particular bit of field work, but have you ever been attacked by a hippo or an orangutan or a lion?
No, thankfully, not. But we see a lot of wildlife. I mean, on the lake, you have crocodiles, you have hippos. There's a special species of water cobra that only lives in Lake Tanganyika, which you don't want to get bitten by. Um, so there are some dangers associated with wildlife there, but thankfully it's not been any kind of a problem. The the main thing that we fight working in Tanzania is it's quite easy to get sick. You can get malaria quite easily, and a bunch of other illnesses as well. Or it's not at all uncommon. Um, Exposure is really typical because it's quite hot, and oftentimes when you work on the lake on a boat, you don't have a lot of cover, so you can easily get sunstroke. But the main challenge for us is typically wind and waves. Because the lake is narrow and skinny and long, and we go there in the summertime when professors don't have to teach. That's kind of our window to get there. That can be a time for very, very violent windstorms on the lake, which can easily sink boats. And we've seen that. It's thankfully never happened to me, but it happens quite commonly. And so being a person on a boat in that lake can be rather dangerous. And so we have to be very, very careful about how we approach our work because you can easily swamp a boat without much trouble. And so that tends to be the scariest part of it. I've been on the lake when there's been more than 10-foot waves,
Yikes!
and yeah, even in a good sized boat, you get thrown around, and especially with students there. I mean, students are it's hard for them to know. Like I've been to the lake many times, so I kind of anticipate rough waters. But for students, sometimes it's a bit scary and it's a bit shocking. So it takes a bit getting used to, um, but it is a lot of fun when everything comes together. And it doesn't always, I should say, like not every field season is an overwhelming success. There's plenty of times when um, the conditions are too bad to actually get the data that you really want, and so that's like probably a useful thing to talk about that doesn't get talked about a lot. It's going to these places and doing this work is it's not 100% success guaranteed. It's it's hit and miss.
Um, One of the viewers, CalcMass, asked the following question: are some of the locals scared of what you're doing in the field, as much as the opposite? In other words, there's probably some people who maybe are concerned about, you're out on the lake with, you're doing some sort of research out there, or a bunch of people coming from another country into these rural areas.
Yeah, it's we make a pretty big effort to stop at every village on the shore to talk to people about what we're doing, because I think there certainly is like trepidation amongst people when you're living, then all of a sudden you see a large boat offshore with a lot of foreign scientists. It can be quite concerning for people. And so a lot of the time that we spend in the field is kind of community building and networking, right? Just letting people know what we're doing and why we're there. And once you sit down and you talk with people, everyone's quite content to allow us to be there and to do it. But that is a big part of the amount of time that we spend in the field. If we need to core or collect data for 5 days, our field season might be 15 days, because we work in those stops to talk to people to make sure that we can do it safely, because there is concern around strange people just showing up and doing things. People don't always necessarily know what those people are on the boat and what they're doing, so it's important to talk to them because it's their home, not ours. um, and that's a way that for us, local collaborations and working with scientists at the lake from Tanzania is a really important thing. They help us and act as intermediaries between us and the folks living on the lake to make sure that everybody understands what's going on and there's no harm being done and so forth.
Well, one of the things that surprised me when we went to Lake Malawi to do research, so I went out in the field with Meg, uh, one field season at the end of the Lake Malawi research project that we were doing, and the 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 country of Malawi required that we bring a geologist along with us from the Geological Survey of Malawi and pay their salary, which isn't really a big deal. Their salary was extremely, what I would view as extremely small. It was something like $50 a day or something that we were paying to have this person along for 2 weeks. But when we talked to him about that salary, he made more money in those 2 weeks that we were in the field with him than he had made for the rest of his entire year. I mean, that $50 US a day, which doesn't really seem like a big deal to me. I mean, I don't want to hemorrhage $50 a day at home, but I would say that,
Sure.
like, but that's definitely not. 2 weeks of that is definitely not anywhere near anyone's salary for a whole year. So
Right.
is similar. Is that similar in around the Tanzania side?
I would say so. I would say so. We do the same when we bring scientists from the Fisheries Institute, for example, with us. We pay their per diem rate, and yeah, I think it is high relative to what they might make normally, um, and of course relative to the people who are physically living on the lake and living off the land there. It's incredibly high. That amount of money is considerable.
All right. So for this particular field season, can you just sort of talk a little bit about what it was like?
Sure.
The one that sort of
The
responsible for the research that collected these cores that are in the Science Advances paper.
Yeah, that was. It was one of our last field seasons. We had gotten an award from a group called Geoscientists Without Borders, which was um, basically a foundation that was established to do kind of science in the service of humanity, and particularly geoscience in the service of humanity. So we were out trying to collect cores in support of that work, and it was the summer of 2017. And so people will remember that because it was the summer when there was a lot of marching for science going on. And we had our own little March for Science in Kigoma of, I think, 4 people. So that was really, it made a mark because that picture got more attention on social media than probably anything I've ever done before. But just
Just
prior to,
just wait till this Twitch interview hits.
hey, yeah, I mean, it's escalating. But yeah, so we went out, and it's about a 2.5 day trip by boat from the port that we start in down to the southern end of the lake. The lake is huge, right? So just getting to the place where we want to core is a challenge. And so it was a long transit down. It was very hot that summer. Um, it's the winter in the southern hemisphere, of course, but it's still very hot for someone like me. Um, and the waves were absolutely terrible. And so our when we got down to the southern end of the lake, there's not a lot of well protected bays. Typically, what you'll do if there is a lot of waves on the lake and you can't work, you'll kind of pull your boat into a bay and try to wait for the winds to drop down so you can get a little bit of shelter. But there's not that many bays in the southern part of the lake that are deep water enough to have a big boat in them. So we got pounded day in and day out by the waves, and we ultimately wound up coring at night a couple of times because the winds would drop down a little bit when the sun went down. And the core that made it into the paper, we actually collected during the day, and we collected a couple of cores from that site. And I knew as soon as we had gotten the core on board that it was going to be an awesome core, because you could see the mud just right through the liner. The liners that we use for the core are like basically see-through PVC plastic, and I could see the laminations in the core, and I could see the tephra layer that shows up in, I think it's the first figure in the paper. And one of the things we've been thinking a lot about for kind of greater science on Tanganyika was trying to find tephras in cores, because tephras are really awesome for dating and establishing chronology. So I knew as soon as I saw the laminations and the tephra that we had happened upon something really great. And so I was super excited about that. And that was sort of in the middle of the cruise. And so you always have a lot of fear on a cruise like this that the cores will actually get back to port and then get back to the United States safely. So there's a lot of kind of built-in stress once you get the core on board. Like, you can kind of breathe a bit of a sigh of relief. And then like getting it back to the US is kind of like the next big hurdle. So there was kind of some dicey moments a part of all of that, but thankfully everything worked out. We were able to work on that core.
So, two notes.
Mm-hmm.
One is that Tuma is here in the channel, and Tuma is the scientist who was responsible for analyzing the diatom record from this lake. I assisted him, but he was doing most of the analyses. And Tuma works as a fisheries researcher on Lake Tanganyika before he came to the US to start working on his master's degree at the University of Arizona. And he said that $50 per day is actually higher than what he makes typically as a researcher when he gets taken out on, so that's actually probably, something that was negotiated by, the Malawi Geological Survey or something. But
Yeah.
so the other thing is you used the word tephra, and
Mm-hmm.
our audience may not know what a tephra is.
Oh, okay. Yeah, that's a good point. So tephra, there are volcanoes in Eastern Africa, and in the Rift Valley that Lake Tanganyika is in, there are some volcanoes to the south. They're past the southern end of the lake um, by a couple hundred kilometers. And when the volcanoes erupt, of course, you get like a big spew of ash and steam and gases into the atmosphere. And some of that material, the ash, gets carried on winds and ultimately will deposit in the lake. And that's what happened in this case. There was a eruption from a volcano just north of Lake Malawi, and that material basically got blown to the north and wound up at our coring site. So we were able to collect that, and those features are important in stratigraphy because they tend to be very, very reliable markers in time, right? We can know very precisely when the volcano erupted by doing some geochemistry and some dating of some of the materials that come out of the volcano. And of course, it's almost an instantaneous event, right? It happens over a very short period of time, and so they tend to be very good chronological markers in sedimentary records, like the one that we got from southern Tanganyika.
And the laminations that you were talking about, I put up a little on the image next to us. I opened up Figure 1 so people could see the the lake itself with its bathymetry is the panel A, and it shows the position of where that lake is located in Africa for anybody who doesn't know. And then bathymetry is the depth below the surface, so the bottom of the basin, and elevation is above the surface of the lake, basically. So the typical sort of topography, bathymetry are those two different aspects, and then there's an image of the core and an age model to the right of it, and you can see very clearly in those in that image of the core the laminations, which are basically the lighter layers, and also there's an area that's marked with the tephra, which Mike said he could see when he could look through the liner, both those laminations, which are the light and dark bands, and the tephra itself. So what's special about having laminated material like this, that made it so that you knew immediately that this was going to be a good core?
Yeah, that's a great question. So um, it's not so common to collect cores that have very well preserved laminations. Um, there's a lot of different. Lake Tanganyika has been studied for more than 100 years. People have been trying to collect sediment from it. Um, but seeing the type of laminations that I could see through the liner, I knew that they were diatomaceous, and I knew that they were going to be able to tell us something about how the lake's food web um, was responding to environmental change, right? So diatoms, and Jeffrey, you can talk about this far better than I can, but diatoms are one of these important microfossils that we use to learn more about processes that are happening in the lake, particularly at the base of the food web. And so it's really nice to have finely laminated sediments because they're capturing very specific and very short intervals of time that can give us like a very detailed window and look at what's happening in the lake. And hopefully from there we can reconstruct why it's happening.
Yeah, so I mean, primarily these sort of light bands that you can see in the figure are dominantly layers that are just diatoms, like the skeletons of diatoms. And of course, in this channel, we talk about diatoms all the time. They're a type of microscopic algae with a siliceous skeleton cell wall. And those light bands that you see that are on there are, diatoms are silt sized particles. They're in the microns size. And to make units of sediment that you could actually see that are just entirely diatoms, that takes a lot of diatoms to do that. And then the alternate bands that you can see in there, the dark bands, are organic rich laminations. So it sort of alternates back and forth between high diatom productivity and then something else that's making the other organic matter that's there. So Calc Math asked, did you disrupt the laminations around the point you collected? Or they want to know if they're using the term laminations correctly. So when you push the core into the sediment, is there some disruption, or are those little wavy bands that you can see just natural?
it there's a little bit of both in there. So when we collect the sediments basically by gravity, we basically drop a tool into the mud, and depending on things like water content and the composition of the sediment, you can have some disruption from the core itself. So when the core enters into the mud at the bottom of the lake, you can sometimes disrupt mainly the upper layers, right? The stuff that's right at the transition from the water to the mud. And that's actually what happened in the case of this core. The uppermost layers got disrupted by the entry of the core into the mud. Deeper down, where you see the kind of greenish diatom layers and kind of the brownish muddy layers down towards the bottom of the core, there seems to have been relatively little disruption there. So those laminations, they're dominantly flat, and they're a little bit crinkled in places, but there's probably not too much disruption. Maybe a little bit of compaction from the core, but that's typically what we would anticipate they would look like as they reside on the lake floor.
So one of the things that makes laminations really important for us is they tell us that the sediments haven't really been disturbed very much. So you can see the bands that are there when they're preserved. It tells us that there wasn't anything burrowing in the sediment or disrupting, naturally disrupting the bottom sediments. And the value for them is that oftentimes they are annual in nature. Are these annual bands? Do you think these are actually varves?
They could very well be, based on the dates. We have more dates from the core now than when we published the paper, but it's likely some of them are reflecting very short periods of time, like transitions between seasons.
And the little wiggles that are off to the right of the core, which are like purple blobs. What are those purple blobs representing?
Oh, yes. So those are horizons that we dated using radiocarbon, right? So there's a couple of opportunities for dating sediments, and relatively young sediments that are rich in organic matter. We can date using radiocarbon, which is one of the typical geochronometers or tools, for lack of a better term, that people use to try to figure out the timeline of different events over, say, the past 50,000 years or so. There's a couple of different tools that are available to geologists for this, but that's one of the really great aspects of working in lakes is lakes tend to accumulate lots of organic materials, that would allow us to actually try to get a date that would be successful. So that's what those purple blobs are to the right of the core.
And then Calc Math asked, how is the gray and red dotted model for the age actually determined?
So it's determined statistically. And so basically what's happening there is, we use a program that models many thousands of iterations of an age model based on the information that we give it, which is the location of particular dates, the age that's been determined by the radiocarbon analysis, and an error bar. And so what those lines are representing there is the model's best fit solution for a regression through those data points. And the gray line, or the gray area, represents the error window, right? So within that area, we may have a potential solution, and the dotted red line is the best fit, or the mean of the most likely outcome for the age model exercise.
So, like, some of the purple blobs are way outside of the bracket for the error, um,
Mm-hmm.
but do you still think those are reliable dates?
There's the one that's right below the tephra is a little bit outside of the error window. The rest of them are at least touching their error window, and so we've since gotten some more dates, and that age remains an outlier. Where we have new dates are basically between 30 and 100. I think there's like 5 or 6 new dates, and they all kind of fall within the window that we would anticipate based on this model. But that one date seems to be still an outlier.
So let's talk a little bit about the relevance of the paper. So the general uh, concept for the paper is about food security. What do you mean by food security?
So, food security is a term that we can think about from the perspective of the availability of food resources to a group of people, right? And so, for the folks who are living on the shores of Lake Tanganyika, their ability to have reliable food supplies is very much linked to the lake itself. Okay, so the way that people get food in this part of the world is primarily through fishing, right? It's the fish are the dominant protein source. So a lot of health and nutrition center around the fact that fish are available and indeed readily available to the people that are living there. And so the security of that resource relates to its availability and how reliable the delivery of food will be to the population that's living there. And I should say that the population in this part of the world is rapidly growing. And so part of the reason why this study is kind of interesting and potentially of some importance is that it kind of highlights the potential for rapid changes in the food security for people that rely on fish in this part of the world.
And there's a question from Tuma.
Okay.
I don't know if he's trying to crib answers for his actual paper that he's writing or what's going on here, but he wants to know, by looking at the core, can we generally conclude that there was more primary production at the bottom of the core than at the top,
Interesting question.
based
What do
on
you
the
think,
fact
Tuma?
that there's laminations at the bottom, but they're not as distinct at the top?
Yeah, it's an interesting question. And this is probably one, Jeffrey, you should probably weigh in on. It's very hard from at least from a geochemical perspective to really suss out like rates of primary production from bulk geochemistry. Um, Now, what do you think? Do you think that towards the bottom of the core, the conditions were higher primary production? I would presume yes.
Well, just based on the fact that you have more diatoms per, gram of sediment, I would say absolutely.
Yeah.
I mean,
And we also know the
diatom,
nutrients are higher down there too, so it stands to reason that the biomass should be higher.
yeah, in the sense that diatoms are outproducing everything else because the dark units are still being produced by organisms, and just not diatoms, right? So,
Yeah.
like it, I think if the sedimentation rate is basically the same, then yeah, I would say that, or maybe that the bottom has a higher sedimentation rate as a result of having more diatom mass in it, right? So that's probably
Yeah.
higher production.
There's I can tell you I've measured organic carbon content over the length of the core, and the values aren't wildly different between the bottom and the top, although towards the top in the black, kind of the black muds that sit up at the top, those are higher in organic carbon content. Uh, but the whole core is very carbon rich, so it's yeah, probably what Jeffrey suggested is good.
So the paper talks about upwelling and stratification. Can you just give the audience a little bit of information about what these terms mean
Sure.
and why they're important?
Yeah, I can try. Um, so upwelling is a big deal, and it's the process. It's basically the process by which nutrient rich waters that are kind of down in the deep part of the lake get brought up to the surface. Okay, and they get brought up to the surface primarily under the influence of um, winds and wind driven mixing. And so Tanganyika is kind of an unusual lake because it's, as we talked about, it's very long and very narrow and very skinny. And so when dry season winds start blowing over the lake, they blow up from the south and move to the north. And basically, what that does is it piles up the surface of the water towards the northern end of the lake. And so when that happens, it actually allows deep waters to come up to the surface in the southern part of the basin. And that's important because where the algae live is in the surface waters, because algae obviously are plants, and so they require some sunlight, and so they're in kind of those superficial parts of the lake. And when they get this deep, kind of nutrient rich and cold water brought up to the surface, their productivity or their ability to carry out their life processes kind of explodes. And so it's a really important process that allows algal production um, in the southern part of the basin. It's critical for that to really happen and to generate the sorts of sediments that we see towards the bottom of the lake. Now, stratification in lakes generally can result in a number of different ways, but all of them are driven by density in one way or the other. Um, Lake Tanganyika is stratified thermally, right? So there's a very prominent thermal boundary between the upper waters and the bottom waters. There's also an oxygen boundary. As Jeffrey mentioned earlier on, um, the deep waters in Lake Tanganyika don't have any oxygen. They're totally anoxic. And part of that results from the fact that there's this boundary called an oxycline that basically separates well oxygenated waters towards the surface versus deep waters, which tend to be pretty much devoid of oxygen. And seeing like those nice and beautifully preserved laminations is a good indication that you had those types of conditions, at least partially, because it's quite good for preventing like benthic organisms or burrowing organisms that live on the bottom of the lake floor from getting into your muds and mixing them up. And so the stratification part of the story is important because stratification, breaking down and reestablishing, is part of how the nutrient cycle works in Lake Tanganyika that's directly tied to the African monsoon. And so those monsoon winds are kind of the way that, the lake is coupled to the climate system. And so how the life in the lake works and has worked over the period that we were studying it is very much tied to climate through the monsoon system and its effect on upwelling in the basin.
Just a quick note, I got a notification that I got an email from Andy Cohen. So Andy Cohen is another author that's on the paper, and he said great interview. He doesn't use Twitch or Twitter very often, I guess, but he's been sort of lurking around in the background listening to the interview. I should point out that Andy Cohen was my postdoc advisor. He was Dr. Mike McGlue's PhD advisor. He was Dr. Sarah Ivory's PhD advisor, and he is currently Tuma's PhD advisor. So his fingerprints are all over this work.
And he was Mike Sorgan's advisor too.
Oh, right, and Mike Sorgan. So almost everybody in that list has worked with Andy.
Yep, that's a fact. Hi, Andy. I'll give you a smile.
Right. Shout out to Andy Cohen and the University of Arizona, who spawned all of these people on some level. So,
Go Wildcats.
I wasn't there long enough to actually learn any of the sport stuff, but yes, go Wildcats.
That's a safe bet.
In the channel, Mika asked a question, which is substantially lower total abundances of centric diatoms occur with high iron magnesium content in the column, and they wanted to know, could we give an estimate of what kind of swing from peaks to lows are we talking about, I guess with respect to those values, and also that there were multiple places in the paper where we reference ratios of diatoms, but we don't really talk much about the total diatom population numbers. So I don't know if they mean concentration or whether they just mean like we only talk about a few different species of diatoms. I can try to answer the latter part of that question, which is there really aren't the population that we see preserved in the sediments really isn't very diverse. So what you see in the paper is almost everything that really was quite common. And although we simplify some of them down into to ratios, I can scan ahead to that part that they're talking about, which is basically the next figure, where you can see all these sort of wiggles that are going on, and one of them is the iron magnesium, or is that manganese? Sorry, manganese iron ratio. And then there's a centric Knizia ratio that's here as well. and they seem to have matching peaks, right? So why would there be a relationship like that?
So, okay. Let's see. I'm trying to follow along on your Twitch screen as you move it around here.
It's just
And
figure
so,
two.
yeah. Okay. Yeah, you're right. There is a little bit of delay. There you go. Okay. So, if you look at this diagram, I'll only break down each of these little curves and just give you a sense of what they mean, and maybe that the interrelationship will come together. So the uppermost curve there, which is kind of that deep navy blue, is silica to titanium. And so this is all of the elemental data that you're seeing here are from a tool called the scanning X-ray fluorescence system. And it's giving us sort of a semi-quantitative elemental chemistry, right? And it gives us a fairly broad range of atomic numbers. So it gives us a nice set of both major elements and trace elements. And so silica titanium is one of the indicators that we use for biogenic silica or siliceous microfossils. In this case, it's dominated by diatoms. We divide the silica by titanium because titanium is exclusively found in minerals associated with the upper continental crust. And so when we divide silica by titanium, it kind of takes away the detrital component or the terrigenous material that might be coming into the lake and just gives us a signal of the biogenic silica or the opal. Going down on the graph, the iron to manganese curve is the one you see in orange. And so iron and manganese are both redox sensitive elements. And so we're using this to track the nature of the redox boundary within the lake. And that's important because we're trying to understand changes in stratification and upwelling. And those processes tend to influence the nature of oxygen within the system. And so this core was collected from fairly deep water by Lake Tanganyika terms. It's like almost 400 meters deep was the coring site. And of course, today that site is anoxic, right? There's no oxygen down on the lake floor. But when we see evidence of change in that curve, it's giving us some indications that that redox boundary may be changing. So there seems to be a kind of an inverse relationship between the silica to titanium curve and the iron to manganese curve, and that suggests that when we have upwelling, right, we might be seeing evidence of ventilation or oxygen making its way down to the coring site. Whereas in contrast, when the iron to manganese curve is high, it's indicating more stable stratification that may be associated with a system that's less prone to upwelling and less, of course, sort of rich in diatoms at the same time. The next curve down, the red one, is the centric to Knizia curve, which Jeffrey, you kind of talked about a little bit. And so if you want to fill in the gap there, that's
Sure.
cool.
Sure. I mean, really, what you're looking at is a record with the Knizia bloom in the lake when there's nutrients available, and when there are a lot of nutrients available, they will quickly consume those nutrients and create a very massive bloom of Knizia. They also bloom in periods where there's not as much nutrients, but what happens is they're very lightly silicified diatoms, and as they sink through this mile deep water column, what happens is they start to dissolve. And in different areas of the lake, what will happen is the Knizia basically disappear before or shortly after they reach the bottom of the lake system. And so they bloom at the surface in the light. They start sinking through the water column as they age, and then when they, by the time they get to the bottom or before they get buried, they are completely dissolved and there's nothing left. The other diatoms that are representing the other half of that ratio, which is the centric diatoms, in this case there's two species that dominate in most of Tanganyika's sediments, and that is Olicosyra, the genus Olicosyra, and the genus Cyclostephanos. And they have more robust skeletons. In other words, they have more silica on each skeleton of the diatom. And when the other diatoms dissolve, these diatoms get left behind. So even though normally we would think of those diatoms being representative of periods when there's even more nutrients. In fact, when we see them in the record, they're largely just a representation of what we call taphonomy. In other words, the preservation of the skeleton rather than actually what's going on with respect to the lake. So when you preserve Nitsia, you're preserving a high bloom or abundant blooming, and that is usually associated with upwelling. And so what that curve is really showing you, and the reason that it seems to match the other curves, so it matches the manganese iron ratio or iron manganese ratio, is that in periods of high stability or stratification, you end up with a bunch of these diatoms that don't completely dissolve. And when you have periods of upwelling, where that curve basically is on the bottom end, you see higher total amounts of silica, which is the top curve, and you also see that it's dominated by Nitsia, which means that they're just blooming, and they're blooming in high enough abundances that they're not dissolving. So you're just seeing sort of a representation of that story reflected in this ratio. The reason that we didn't put in the rest of the story is, one, Tuma is writing a paper on the rest of the story, and two, the curve itself is really telling us what we need to know about upwelling and stratification, and it matches our other bits of data pretty well. So for these types of papers, in Science Advances, you're given just like a real small amount of space, and you have to kind of compress your figures down. We simplify them into these ratios and then basically just show the ratio. Later on, Tuma has a paper that's basically getting ready for submission, and he will sort of display the rest of the diatom story in that paper.
Right, exactly. So that'll be one to look for in the future.
Yeah, and maybe we'll have Tuma on to do an interview for that one.
Yeah, exactly. And so the other geochemistry on there, let me switch back to my screen so I can see it. The yellow dots are nitrogen isotope data, and so those notionally are tracking the presence of cyanobacteria, which fix nitrogen in the water column. And so we tend to find those in association with strong upwelling because it's giving us, there's an association between these types of cyanobacteria, blue-green algae, and the diatoms that Jeffrey was talking about, the Nitsia. Basically, they come around towards the end of the seasonal cycle when upwelling is strong. They could take advantage of some of the conditions, the chemical conditions in the water column. And then down towards the bottom of the diagram there, the last data set that we have is phosphorus, which is giving us indications of nutrient burial in particular, and how that varies through time in the system. And you can see it tends to be highest when we have intervals of very strong upwelling, which are the gray shaded boxes, the vertical boxes on the diagram.
So a couple of questions from the audience. One of them, some of them are about the terminology. I noticed you used the word terrigenous, and Pacific Plankton asked what that means.
Okay.
Just means from the land rather than from the water. And Volcano Doc, welcome to the channel. Volcano Doc is another geologist that streams here on Twitch. And they actually have a question. I'm gonna actually stick in Calc Math's question first. What do the gray bands represent?
On the diagram you're talking about?
Yeah, in Figure 2.
Yeah, so I think that the gray vertical bands there are what we infer to be periods of enhanced upwelling. So typically the gray bands will coincide with peaks in silica to titanium, troughs in the iron to manganese, and some of the other the peak, like higher values in phosphorus and ultimately lower values in nitrogen isotope. That the one vertical scale in the nitrogen isotope data is reversed. All the other scales increase up, but the nitrogen isotope scale decreases up. So those values moving towards the top or lower on that particular panel.
So they're just there to aid your visually to aid so that you can see where the curves are all basically showing transitions, right? So it's like
Yep.
it's just like a clue for us. When you look at the graph, you can say, oh, I see we're in a light band, because when you have all these wiggles and they're stacked up like this, it makes it challenging for people to figure out what you want them to notice about the data. And putting just a few simple bands on there like that oftentimes basically highlights that for people. So Volcano Doc asks this question: do you think that the variations in oxygen fugacity could be due to changes in magma flux below the ERZ?
I okay, so ERZ would be East African Rip Zone, I'm assuming.
I think so.
Okay, I suspect probably not, given the time scales that we're looking at. So we're looking at a record over a fairly short period of time in the recent past. So my guess is that the volcanic activity that might potentially influence oxygen, pardon me, fugacity, would probably be operating over longer time scales than we'd be able to discern in the record.
Can you help people with what fugacity means?
Oh gosh, so
We could make Volcano Doc answer that in the
I
chat, I
was gonna say
suppose.
that should be a volcano doc. It's basically the ability of the ability of something to move around effectively, right? It's basically how oxygen is getting partitioned within or and among environments.
I thought it was a band from DC from the 90s, but what do I know? All
That's
right.
right, isn't it? Is that what you think? That's what fugacity means, isn't it?
That's right. It's the DC Fugazi band. Um, let's see. Mika is asking another very specific question, which is, could you
Okay.
explain in a few words more on the first half of the second paragraph on page 4, dealing with the nitrogen 15 data? So he said these are the most difficult sentences for them to understand, which is basically what's going on with the delta N15 values. What are they really telling us, and how do you interpret them?
Okay. Yeah. I don't have that. I don't have the paper pulled right up in front of me, so I'll try to
It,
wing it
it's
based
it's
on.
creeping up. I got it on here now for you. It'll just take a second to get there.
Okay.
I think it's this
So
occurring cyanobacteria.
okay. In a nutshell, the nitrogen data, we we use nitrogen data to well, we use it in a couple of different ways, but one of the ways that it's often used is looking at changes in algal composition, right? Like changes in the type of algae that are in the lake. And it tends to be reasonably good at discriminating algae that assimilate nitrate versus those that fix nitrogen. Okay, and so the values that we see here in this core, particularly ones that are very, very low, from say like, around 0 to less than 0, those tend to be values that signify nitrogen fixation within the water column, being carried out predominantly by cyanobacteria. Where those values creep higher into the 1, 2 per mil range, we tend to interpret a mixed algal signal that has a greater capacity for nitrate assimilation at those times. So we're really looking at partitioning of nitrogen within the aquatic system, and the types of nitrogen species that are being utilized by the different types of algae that are present. And so that's a bulk measurement. It's not made on any particular molecules other than bulk sediment that's been actually it's not been acidified. It's just untreated sediment. The problem with doing nitrogen isotope measurements is that nitrogen is very labile, and any sort of pretreatment that you do to the sediment can actually fractionate the isotope or remove nitrogen from the system altogether. So when we do nitrogen isotope work, we tend to do it on untreated sediments.
So I would add in one thing, which is maybe a little opaque to people who aren't familiar with algae, which is that cyanobacteria have this specialized skill called nitrogen fixation, which allows them to take nitrogen gas, which is N2, and normally that's inert. In other words, it's normally something that's completely biologically inaccessible, and and turn it into something that other organisms and themselves can use as a nutrient. So the rest of the organisms, diatoms, green algae, cyanobacteria that don't fixate nitrogen, they are reliant on the nitrogen nutrients that are available in the water. And if they don't have those, basically they starve for nitrogen, and it usually causes the population to shift from one type of algae to a different type of algae. So when you get blooms of cyanobacteria that can fixate nitrogen, it means that that system has probably already been starved of nitrogen, and these things then become the dominant species. So, just as a little bit of sort of like a background for making that make sense, usually stratification in lake systems leads to starving the lake's upper waters of nitrogen. And so the link there is really that stratification typically results in nitrogen fixation being a dominant force, and upwelling typically results in a release of nitrogen that's stored in the hypolimnion and the bottom waters of the lake, and recirculating that and allowing it to be accessible to the algae, which are up in the upper part of the lake where the light is. So does that
Yeah,
make sense?
fixing nitrogen is not something that all algae can do. It takes a lot of energy to break those bonds. Like to break an N2 bond is quite an energetic process, and most algae can't do it. And so it gives us a way of discriminating amongst different types of algae and when the conditions are met.
Yeah, I would actually argue technically no algae can do it, only bacteria, because
Only
cyanobacteria
bacteria.
not technically algae. We think of them as being algae.
Mhm.
So there's a question in here, which I think is actually really a good one that Pacific Plankton asks, which is, can agriculture mess with the data? Because people have learned how to fixate nitrogen, and we can add
Yeah.
nitrates to the land surface. And one of the associated problems with the area is, of course, that they're converting a lot of the surrounding land into farmland, right?
They are, but not immediately near this coring site. So most of the heavy agriculture that we see around the lake, um, this part of the lake margin is fairly high relief, so it's quite steep on shore, adjacent to the areas where we were working. So there's not a lot of there's very few large villages in this particular part of the lake. So I'd be less concerned about agricultural effluents influencing the nitrogen system where we're looking at it here. Now that being said, there have been studies that have shown like a strong soil contribution of nitrogen that has affected nitrogen isotopes in shallower water areas to the north. So that same isotope has been used to actually pinpoint the agricultural contributions in different parts of the lake.
So the next question is also from the chat, which is a really good one. What is the phenomena that's driving the variation that we observe in stratification versus upwelling? So what is the process that sort of leads you to either get more stratification or more upwelling in the past?
Yeah, I think that's the coupling that we're inferring here is changes in the monsoon system, right? So the monsoon, as it affects the lake, really does influence the development of seiches, which are basically internal waves within the lake that occur when you get this strong and persistent wind blowing in one direction, that allows and in fact fundamentally changes how mixing occurs in the upper part of the water column in the epilimnion. And so the variability in the monsoon is a key factor here in changing the nature of the upwelling system. That's certainly one big one. The other factor that seems to have a big control on the nature of stratification in the lake is water temperature, right? And so the temperature of the water, if you can imagine, if you wanted to strengthen stratification, and the stratification is generated by a density difference due to temperature, if you heat up the surface waters, that's a fairly effective way actually of strengthening the stratification. And so there's a temperature effect here that's also discernible in the geologic record as well.
Yeah. I think you kind of answered, hopefully, Mika's next question, which is there in chat, asking about what's the primary effect of enhancing the temperature of the water. Why does that actually cause this sort of system to reach a tipping point? Where it might affect productivity and food security. So if you make the water temperature warmer, basically you just enhance the stratification, which then limits the nutrients that come to the surface and limits the total productivity. And then if there's no food for fish, then you can't make fish, right? You need to have some resources there, so they're linked together with the diatoms and the other algae, which are the primary food source. And so that's really the connecting pin that sort of links all those things together. If you don't have food, for the fish, which is what the upwelling, is producing, then you don't have fish for people. So you affect the entire food chain.
Yeah, it is a chain or a web, and that's exactly right. They're linked through those intermediate steps, going from the algae all the way up to the predators in the system, which are the large fish that people eat.
So there's two questions here that I think are really good ones. One is calc math. Is variation in monsoon implied by your data corroborated by data from other sources?
Yes, it is. So we've done the way that we were able to infer some of the mechanisms driving changes in the monsoon was our colleague Sarah Ivory did some modeling of recent climatological data that showed linkages between, for example, the cold phase of the ENSO system and monsoon wind strength over this part of Eastern Africa. So there's a fair amount of modern climatological data that helps corroborate the story and the mechanism that we're invoking for changes in production in the lake. But have there been, perhaps a related question is, are there similar studies from Tanganyika that have showed this? And from Tanganyika, there's one study that was published more than a decade ago now that the data were lower resolution than the data from this particular core, and the core was situated farther to the north, so it was a little less sensitive to the upwelling system within that core. And that data set was published in 2005 or 2006, and there was some indications in the data that solar cycles were playing a role in influencing the nature of sedimentation, but because of the temporal resolution of that study, the mechanism was equivocal. And so there have been hints in past data sets from Lake Tanganyika that maybe solar irradiance could play a role in influencing algal production, but it hadn't been demonstrated until our work.
So yeah, you can see that's basically what figure 3 is sort of talking about. It's showing our data's here at the bottom. It's showing the really high resolution silica to titanium, which is showing diatom productivity. And then the El Nino La Nina cycle, what's called the Southern Oscillation Index, which is in red and blue here. And then above that was the record that I believe Mike was talking about, which was Jess Tierney's record, which is looking at reconstructing the surface water temperatures using geochemical methods. And then above that is the sunspot activity record. So these yellow and purple sort of curved things up here are periods in the past where there was high solar irradiance, or a lot of energy coming out of the sun, versus limited energy coming out of the sun. And you can definitely see there's some, or appears to be some, link between this Spoorer minimum and sunspot activity and these lower temperatures associated with it. And maybe also a nice link here in the Wolf minima, and also here in the Oort minima for sunspot activity. It doesn't look like it works very well at the surface, but this information is much lower resolution. In other words, you can see we have maybe hundreds of wiggle for each one of the wiggles in that record up there, based on the scanning XRF data from our core. So Pacific Plankton asked, does oxygen drop? Why does the oxygen drop when the water gets hotter?
Okay, yeah, that's good. So the colder water basically stores more oxygen. That's a simple way of saying it. So cooler water can hold more oxygen than warmer water can. And that's just a kind of like basic physical chemistry of the water itself. And kind of linked to that is there have been some other studies on Tanganyika that have shown movements in the position of the oxygen boundary, and those seem to be strongly linked to surface warming of the lake itself as well. So there's a couple of different ways that physical character manifests itself and how the lake can function. And so that one of the worrying trends that have been observed in Lake Tanganyika is the shallowing of the oxycline, right? And basically that's just a fancy way of saying that the areas of the lake floor that are absent of oxygen are actually growing. And so part of that relates to climate related warming of the surface waters.
So CalcMath asks a really good question as well here, which is, isn't the El Nino La Nina cycle around 7 years for the cyclicity? And then what is this graph actually depicting? So the x-axis is in hundreds of years.
Which graph are we talking about here?
I think the on figure 3, the El Nino La Nina curves.
Oh, sure. So the inference and the El Nino La Nina signal within the data is derived from statistical wavelet analysis, and so the ENSO periodicity it doesn't center necessarily on 7. It basically covers a range of 2 to 12. And so when Sarah Ivory, our colleague, who is one of the authors on the paper, she worked on the statistics trying to get at some of the cycles or some of the beats that might be inherent in this very high resolution silica data set. One of the ones that pops out is that El Nino beat, like the 2 to 12 range is significant over several intervals of the core, most specifically when solar irradiance is also high, right? So there seems to be a coupling here between solar irradiance and ENSO, and that's what the figure 4 is showing. We can't, the X time scale on figure 3, we're showing the full frequency of the record in time. And so the cyclicity that's inherent within the data set is brought out by that statistical analysis that's represented by figure 4.
So obviously we don't have a Southern Oscillation Index curve that goes back thousands of years, but it's a inferred changes in the main sort of state of El Nino La Nina, I think that this is showing, right?
Yes, the SOI curve, that's kind of the third one from the top on figure 3, is effectively a compilation of several different paleoenvironmental reconstructions of the ENSO system. That comes from coral data from the Pacific. Basically, people drill into corals and look at the coral banding and see how coral growth responds to changes in climate. There's a record from the Galapagos Islands that a graduate student at Arizona worked on when I was a graduate student there. She's a professor at Illinois now, Jessica Conroy. Professor Conroy did that work. She looked at a lake record and sand layers within the lake in the Galapagos that was also sensitive to precipitation associated with El Nino. And so that's what that curve is there. It's a compilation of several different El Nino reconstructions. And we should probably mention that El Nino reconstructions are not super common, particularly at high resolution and particularly over broad area intervals of time. So having this data set available was super important for thinking about what's controlling the limnology of Lake Tanganyika.
So we've hit on most of the figures. I would say whenever I tell my students to read a science paper, what I tell them to do is just look at the pictures and figure out what the figures are trying to tell you, and then you'll understand what the paper's about, unless it's a bad paper, in which case the figures don't do a very good job of explaining that. So I think, we've reached sort of the that sort of saturation with respect to what we could talk about from the research itself, I think, unless you have anything else you want to sort of add to that. We have the timing is sort of in this range of a variability that we see is sort of El Nino La Nina frequency, and then our assessment of that in terms of what it means. So what does it mean for food security which is basically what the premise of our paper was.
I think that the big takeaway message that I would want people to leave with is that this system has the ability to change rapidly. And I think that's something that is has not has been thought about and speculated about, but there hasn't been a lot of data um, to drive management decisions around that notion. And so, what do I mean by that? There's I think a really nice line in the paper that kind of Sarah and Jeffrey and I crafted together that basically says something to the effect of, in order for science to be effective for conservation or for fisheries management, the time scale of the observation needs to be something that humans can relate to. So basically, it means that if we want to protect the fishery and build resilience within this system that's providing food to so many poor people, we need to have observations and data that are at very finely resolved timescales, like something that's relevant to a human lifespan, say, years to decades to maybe a century. And prior to this study, those types of data sets were very, very rare from Lake Tanganyika. Even though there's been really awesome science published from the lake, most of the observations were at the scale of several thousands of years. And so what this data set is important for then is, I think, giving a very fine time resolution to a system that has big implications for how people access food. And so we've made the point in the paper that the potential for the system to change over very abrupt and short timescales is clear and obvious in the data set that we have. And so that's where I think the impact of the work will come for food security. What do you think, Jeffrey? Does that get to it?
Yeah, yeah, I think that answers that. There's a question in the channel that I think I should probably take on, which is,
Okay.
if diatoms are continually taking silica to the lake bed, burying it basically, but there's evidence that silica remains, as evidenced by the fact that we still have fossil diatoms being produced constantly, is the total silica that's recirculating decreasing over time? And can upwelling bring the silica back to the lake supply if the upwelling only reaches to about 300 meters below the surface, right? So we have a super deep lake, we bury the silica, and is there a possibility that some of that is being basically sort of sequestered or removed from circulation? And then, how do you keep making diatoms in that scenario? So there's actually a whole series of questions in there. I would start by saying silica is constantly being recharged by rivers that flow into the lake system. And there's dissolved silica in the form of just loose silica that's in an ionic state, or a soluble reactive silica that's in the water, as a result of phytoliths and diatoms that are being dissolved in the river systems, and also some contribution from the land surface. And that recharges the amount of silica that's in the lake. So the lake is not a completely closed system. In fact, it's quite the opposite. It has major rivers that flow into it, and they bring nutrients into the system. So there's not a finite amount of silica in the system. You shouldn't think of it that way, but there is a cycle associated with it. And if you stratify the lake system for really long periods of time, you can force silica to be sequestered. But it's actually easier to sequester silica because the stuff that's stuck in the hypolimnion in the bottom waters, it probably eventually will get advected somehow or pulled up from the hypolimnion somehow. But the easier way to do it is to actually bury it by having a bunch of blooms at the surface. So the linkage is actually upwelling causes burial of things like diatom skeletons. Otherwise, when you have stratification systems, you still get some nutrients every year that basically get fluxed back to the surface. It's just that they are essentially dissolving before they get to the bottom, or shortly after they get to the bottom. So one of the things that's not completely transparent is that the upper waters are circulating in the top 300 meters. There's a giant convection cell in lake systems that gets established, but the hypolimnion is actually circulating usually in the opposite direction. There's actually large convective cells that occur in the hypolimnion as well, because there's some drag at the boundary between those two water bodies, and that actually causes the hypolimnion to also circulate. And that means nutrients like silica and whatever else, phosphorus, nitrogen, whatever else that's available in that water, effectively can get pulled up from great depths, even though you're not actually circulating the water from the surface all the way down. So that boundary between them, you can think of it like a conveyor belt, is pulling a little bit of nutrients every time it comes towards the bottom. And if you get substantial upwelling, you'll basically just cut into that boundary a little bit deeper. And if you get substantial stratification, you basically just isolate that body a little bit longer. And so those two things kind of play together. There's a cycle associated with it, which clearly my daughter has got a PhD and is answering questions in the channel, or that's my wife who's taken over control of it. There are biogeochemical cycles associated with the silica, and the sort of upwelling and burial and then addition of silica from the land surface are really kind of important. Yeah, evected is just a fancy word meaning like sucked up from the bottom in a like a convective cell, right? So like you have the circulating water, it basically just pulls up some of the nutrients because they're free floating in the water column. Okay, I think that answered that question. If not, you can always check in our Discord later and throw questions at me, and I'll try to answer them. So Anarchy Kitchen says, what are the implications of the lake being capable of rapid changes on food security terms? And I would actually argue that one of the things that's maybe not clear from well, it's underwritten in what Mike was saying is that we're talking about this massive lake system, like one of the largest lake systems on planet Earth. And one of the underlying ideas that people have is that the larger your water body is, the less likely it's going to respond to changes. So if you had a puddle and you dump a bunch of nutrients in the puddle, you'd expect an immediate response from the puddle. But if you had a larger system and you dumped the same amount of nutrients in, you'd expect that it basically wouldn't have as big of an influence. And if you put it in the largest freshwater body on planet Earth, or one of them, you'd expect that it probably wouldn't have that much of an influence. But I think what this results are showing is that just as people have observed in the ocean, we are having an effect on these bodies. And even though we used to think of the oceans as being these immutable systems and large lakes as being these immutable systems, that they can change, and we are helping to produce those changes by modifying things. Let's see. So I'm going to move on and throw out one more question. So I want to ask, what's it like publishing a paper in something like Science Advances? Because people probably aren't aware of why it's a big deal. Like your average person doesn't know one journal from another. So what has this sort of process been like for you, Mike? Because you're the lead author on this big paper. What's the big deal? Why is Science Advances a big deal?
Well, it's a little bit different than some journals that we might typically publish in. A lot of the times, our studies will get published in what we would think of as discipline-specific journals. So in other words, the target audience is other scientists who do similar things to us, right? And that's kind of, a very typical pathway for a scientific paper to be published. A journal like Science Advances, or one similar to it, there are others. The audience for that type of a journal is really everyone, right? It's meant to be quite a broad audience. And so in order to get a paper published in that type of journal, the story has to be one that could appeal to someone other than people like Jeffrey and I and Sarah, who actually study lakes for a living, right? The idea is that the topic is sufficiently interesting and sufficiently important that, a physician in India might be interested in reading it, or, someone else in Australia might be interested in reading it who's, not doing studies on lakes or climate change or food.
Right.
And so it's
Or a cook on Twitch.
right, exactly. It's meant to be. It's written in such a way that it's accessible to a broader audience, or at least in theory, it's supposed to be. And it's a challenge. I mean, getting papers published in general is a challenge. Let's face it. But that's kind of what we do for a living. And this one was in many ways similar to a lot of the other ones that Jeffrey and I have worked on, and Sarah and I have worked on. It's just that the the writing is a little bit different because it's meant to be for a broader audience. So it's a little bit um, crafted in such a way that would hopefully make it appealing to people. And a lot of what gets published in these types of journals has to do with that broad level of interest. Most of the journals now that are broad interest scientific journals have a lot of articles around COVID-19, for example, right? Because that's a topic that, regardless of what field of endeavor you're working in, you're probably interested in it just from kind of a societal health perspective. And so too is this article, right? It's meant to have kind of broad appeal and interest because of just simply the number of people who live in sub-Saharan Africa who rely on inland fisheries as a primary food source. And so any potential changes in those types of systems have big implications for lots and lots of people. And there's lots of people who are interested in knowing more about that and helping to plan for it: governments, non-government organizations, um, universities. It really runs the gamut. And so it qualifies for the broader interest appeal on those grounds, I think.
So I just want to try to sort of wrap things up. We've been pegging Mike with questions for about an hour and a half now, and I did have one other comment I wanted to sort of bring up because you also very recently were awarded a grant, $1.5 million grant from the International Continental Drilling Program for Lake Tanganyika, and I just wanted you to have a chance to sort of talk about how does that grant and that money link to this research, or does it at all?
Sure. Yeah. Well, I think the that grant is aimed at collecting a very long record of environmental change from this lake, right? And so, as we talked about at the start, Lake Tanganyika is really old, and it's really special because it probably has one of the oldest sedimentary records available to us in the tropics, right? And so the tropics are an area of great interest to the global climate system because a lot of how that system functions is as a result of processes that occur in the tropics. And so a lot of folks like myself and Jeffrey, and actually many of the authors on the paper, in fact, are interested not only in these short-term changes in climate and how they affect the lake, but also much, much longer changes, a much, much longer record that encompasses changes over different timescales. And so one of the things we'd ultimately like to do would be to look at how the lake's upwelling system and how primary productivity has changed over million-year timescales, right? And so Lake Tanganyika is probably the only place on Earth where we could recover perhaps 3 to 6 million years worth of record to study problems like that. And so that grant that you're referring to, Jeffrey, is kind of the first step in making that process happen. Like collecting a long scientific drill core is exceedingly expensive, and so the project itself is probably in the neighborhood of $15 to $20 million total just to recover the cores. And so that award will kind of set the wheels in motion towards a whole host of new grants that will be written and hopefully be funded so we can look at some of these kind of interesting climate lake questions over longer periods of time. And so there's lots of folks who are involved in that, and there's lots of different disciplines that will plug into studying those cores. From fish biologists who are interested in how long evolutionary processes take and what their character has been over the course of the lake's history, to people who are interested in the tectonic evolution of the basin from a geological perspective and thinking about how, at what rate faults move and at what rate space is created within the basin to hold sediment. So there's really many, many different types of researchers who will come together to examine those cores and pursue questions that are specifically interested to them. Sarah, for example, is very interested in terrestrial vegetation, right? The types of trees and shrubs and grasses that grow in Eastern Africa and how those change over time. With changes in climate or changes in the presence of herbivores or things like that. So there's a real diversity of scientists who are interested in looking at those cores and thinking more about the evolution of Eastern Africa and the tropics in general over the past 5 million years or so. And that this record will be one that will hopefully do that better than any others.
I see from the chat channel that Sarah has asked us a very leading question. Can
Okay.
the purported cores tell us anything about what was happening on the land?
Well, yeah, I should say. the,
She cares about the
the,
land because she studies pollen.
Right. Sarah loves plants and not the ones that live in the lake, but ones that live next to the lake. And so the plants living next to the lake can tell us a lot actually about how the landscape evolved and what sort of temperature and precipitation conditions existed over the course of the Earth's history, right? So particularly of the past 5 million years or so. So pollen records from that core that Sarah will study in great detail for the next 35 years will cast a new spotlight on things happening on the land. And we'll look forward to reading those.
Yeah. All right. Well, I want to call it an interview, unless you have anything else you sort of wanted to bring up for the audience. Mostly because it's getting a little long in the tooth. It's been a long day,
Sure.
and I feel like we did some good work looking at the different processes and sort of talking our way through the papers. There's maybe some unanswered questions that people have. If that's the case, I did include Dr. McGlue's email below, and I'm sure he would be happy to answer any questions if you wanted to email him. You can also ask questions to me, or you could drop by the Discord. So Pacific Plankton posted a link to the Discord. I don't know if that's the one that wasn't working earlier or whether it's one that is working, but we might want to double check that. But you can also get to the Discord if you scroll down and into my profile. If you're reviewing this from a computer and click that join the Discord button, there's a chance for you to talk. And there's an unrelated question that I think we could fit in, which is, what was your favorite dish from Tanzania?
That's a great question. I like a very delicious type of cichlid that called kue, which is it's the emperor cichlid. It's probably close to endangered if it's not already.
Because it's so
But it is
delicious.
it's so delicious. There's a reason why it's close to being endangered. But yeah, it's a delicacy, and I love it. I get it every time that I go there.
There you go. If you're interested in reading the paper, it's an open access paper. And if you are viewing this from a computer, laptop, or whatever, if you click on Mike's face on the interview with Dr. Mike McGlue down below, if you just scroll down using your mouse wheel or whatever, and you click on Mike's face, it'll take you directly to the paper. So you could read that. You can also check out my other research, the Discord channel, if you are interested. There was a bunch of pictures that have been going by from diatoms that we've collected from Lake Tanganyika. These aren't just random diatoms that I'm showing that are on the side here. These are actually species that are found in Lake Tanganyika that we've put onto. Yeah, you can get there somehow. That we've imaged on my scanning electron microscope. If you're interested in checking out what we normally do here in the channel, which is I usually put some sort of a microscope thing on there, and we look at it. You can easily do that. For scanning electron microscope stuff, I usually stream on Wednesdays and Saturdays from 1 to 3 in the afternoon. And if you're here because you're really excited about microscope stuff and instead you got a super cool interview with Dr. McGlue, you can always check those out later. Also, we have a whole bunch of friendly microscope streamers that are here in the channel with us that you've seen gone by. And I'm just going to send them a little shout out by using my squad command. So you can check out any of these ones. Pacific Plankton, who's acting as our moderator for the channel, OpenSet, and Del Maximum, who were both here earlier, asking questions or interacting. So you should definitely check any of them out. They have great, interesting science-based or nature-based streams that I think are really engaging. So with that, I think we'll call it an interview. I'd like to thank Dr. McGlue for spending the evening with us talking about his paper, and also Dr. Ivory for hanging out in the channel with us, and Tuma, and also Andy Cohen for checking us out. Just a shout out to all of our co-authors. I know that Mike did most of the heavy lifting in this paper for sure, in putting most of the figures together and pulling together most of the text, and then I just sprinkled a little diatom magic on the parts where I felt like I could contribute something. So the most of the work though is definitely in Mike and Sarah's sort of ball court. So thank you, Mike.
Well, this has been fun. Thank you, Jeffrey, and as ever, thank you for your collaboration. It is pivotal.
Yeah.
Pivotal.
Yeah, it's fun. I like working.
It's great.
I like working with you. We get along great.
We've had some good times, right?
Yeah. Probably because you do all of the hard work, and then I do all of the collecting of accolades associated with it.
Hey, that's all good. Well, you guys have a great night. Thanks again for hosting me. This has been a lot of fun.
Yeah. Thanks also for everybody here who stuck around in the channel and who checked us out. This will be recorded, or it's being recorded and stored on Twitch for the next month or something. And then I'll probably also store the interview on some other forum for this one, for YouTube or something like that. I'll provide some information about that later on for people if you missed it or you want to share the interview. I think our department is interested in it as well. So
cool. Yeah, cool. Let me know if you do it. I'd like to link up to it.
Okay. So cool. That's a wrap, I guess. We can go back to talking about hamburgers or whatever we wanted to talk about. All right.
Outstanding. Yeah, that was nice. Yeah. It was really, really fun.
Okay. Cool. I'm going to pull the plug now. Thanks, everybody.
Sounds good.